What's up, guys? Welcome back to the channel. We just heard that, but yes. So we are doing the Unit 10 Water and Solutions review. This is kind of a long test, so it's going to be kind of a long review, but I promise if you can do all of these problems, you'll be able to do all of the problems on the test. So let's get started. Number one, what is the approximate number of grams of each solid that must be added to 100 grams of H2O to form a saturated solution at 70 degrees Celsius? Okay, so this question is asking how many grams do we need to add on to each A, B, C, and D? So there are actually 4 answers to this problem. We have A, B, C, and D, and they're all going to need different amounts of grams of solute to be added on in order for their point to be on the line, which is saturated. So what I mean by that, first we see number of grams of each solid must be added to 100 grams of H2O. So right here we have grams per 100 grams of water. So that 100 is kind of a trick there. We're just looking for how many grams of solid A, B, C, and D need to be added in order to make all of these saturated. But there's another kicker. At 70 degrees Celsius. So that means we can take a line here and draw it all the way up at 70 degrees Celsius. Okay, so at 70 degrees Celsius, we need this point for solid B, this point for solid A, this point for solid C, and this point for solid D. At 70 degrees Celsius, this is the saturation point for A. For B, it's down here. For C, it's right here. And for D, it's right here. Okay, so the hardest part about this is probably just reading and aligning the graph to what it's actually asking. So the approximate number of grams of each solid that must be in 100 grams of water to form a saturated solution at 70 degrees. So now we know our definition that saturated means the point must be on the line. And so we can just put it in at 70 degrees, what is the gram? So if at this x-axis, what is the y-axis going to be in order to intersect with each line? Well, at solid A, we're about halfway in between 100 and 120. So we're going to call that about 110 grams. At solid B, we have to follow this green line down here. Here's 70 degrees Celsius. This point is just above 20, not quite to 30. I'll call it 25 grams of solid B. Solid C, I come right here, 70 degrees. This is about in between 40 and 60. You can call it 50, you can call it 45. On the test, it's going to be kind of a drop down and select. So these are far enough apart that you'll be able to estimate it with ease. And solid D, we go to 70 degrees on the line. That is right above 40. We will call it 41 grams. So maybe this one would be like 50 grams. Even still, there is an obvious difference between these two. And so all this was asking was at what point was each solid saturated? And so we just answered that question. Make sense? Any questions? Number 2. Refer to number 1. When 60 grams of solid D is dissolved in 90 degrees Celsius, what kind of solution is made? A blank solution is made. So I have 60 grams solid D at 90 degrees Celsius. So if I go to 90 degrees Celsius, then I go up to 60 grams, here's my point. Now that I've plotted my point, I need to answer that question in relation to solid D. Well, for solid D, my point is above the solid D line. That means that my point is supersaturated. because it is above the line. Makes sense? If the point is above the line, it's super. If the point were down here, then solid D would be unsaturated. Now, if it had said solid B, then we'd be perfectly saturated. But that's not what the question was asking. So you have to make sure you are using the correct line, which is given to you in the problem, and read it carefully. Number 3. Which of the following compounds is considered a non-electrolyte? Non-electrolyte. So, if we remember, an electrolyte is an ionic compound that dissolves. An ionic compound that dissolves. Or it dissociates and it forms ions in solution. So I'm going to need my solubility table and how to read it. Once I have my solubility table, this question is easy. Now I can give you some shortcuts here, and those are in the notes, but I'm just going to make sure that we know how to read this thing. So, a non-electrolyte, meaning when it dissolves, it cannot conduct electricity in solution. Well, NaCl dissolves and dissociates in a solution. That's salt water, and salt water conducts electricity. If you did not know that, you could look at chlorine. You go to the solubility table, and you find chlorine on here. And you see that chlorine is soluble in compounds that contain it. So if a compound has chlorine, it's going to be soluble. Then I follow over to these exceptions, and that will tell me chlorine is soluble unless it is with Ag or Pb or Hg. Well, thankfully, in this one, we're with Na. So that means chlorine is going to remain soluble and is an electrolyte. That is not the correct answer. Next, I have H2SO4. This is where the handy trick comes in. If O's minus H's is 2 or greater, then we have a strong acid, which is also a strong electrolyte. So here I have O minus H equals 4 minus 2, which equals 2. This is a strong acid, which is a strong electrolyte. So it cannot be the answer to this question either. Next, I have C2H6O. Well, O minus H is a negative answer, and so I can't really use that as a helper, but I can realize that any CHO compound like this, that kind of looks like glucose or really any random numbers, that is going to be a non-electrolyte. It is not going to dissociate in water. Sugar may dissolve in water, but it does not dissociate into 2 ions. It's not possible. This is not an ionic compound. This is a covalent compound. Then lastly, I can look at KBr. KBr is potassium bromide, and I can use my chart for this one. So I can look at Br on my chart, and when I pull it up, I see it's similar to chlorine. Br is soluble, except in compounds of Ag, Pb, and Hg2. Well, Br is not with any of those, meaning it is soluble, meaning it will dissociate in a solution, meaning it is an electrolyte. So it is not a non-electrolyte. So there is our only answer there, C2H6O. Feeling good? Okay. Number 4. Beakers A, B, and C each contain a different solution. The bulb will glow when the conductivity apparatus is placed into which beakers? Okay, this is really asking which of these solutions conducts electricity. Because if the solution conducts electricity, then the bulb is going to glow. If it doesn't, then it doesn't conduct electricity. So it's asking again, which of these is an electrolyte? Which conducts electricity? So NaOH is a strong base. And I put it on here because there's really no way to know that this is going to be an electrolyte other than for me to teach it to you. So NaOH is a strong base, which means it will dissociate completely in a solution, which means it is an electrolyte. If it's strong, it's an electrolyte. If it's strong, it dissociates completely. I look at letter B. Letter B is HNO3, that's nitric acid. If I use my little trick here, O minus H equals 3 minus 1, which equals 2. This is a strong acid, meaning it's going to dissociate into ions, and it will conduct electricity, and the bulb will turn on. So this is also going to be part of my answers. Notice how there may be multiple correct answers. And then I look at strontium hydroxide, SrOH2. Strontium hydroxide, I need to double check, but strontium hydroxide, I'm pretty sure, does not conduct electricity. So that one, actually I can look it up. Yes. So strontium hydroxide is another one that's tricky. That's why I put it up. Strontium hydroxide also is a strong base. It is a strong base. Now, the trick with the strong bases is if you go to the first two rows of the periodic table, and you ignore water or hydrogen. These strong bases make kind of an L shape, where it's most of these in the first column, coming down into the second column, and skipping beryllium. So it kind of makes an L here. And I know that that is annoying to learn, and that's not the best way to teach it. But in terms of this test, it doesn't come up again until our acids bases test, which is the one after this one. So some of these questions are annoying and a little bit out of order, but that's how the tests were created. So if it's strong, it will dissociate. And then these are my strong bases. More on that later. Which of the following is considered a strong electrolyte? So number 5, again, we have NaOH, we have NaOH, which we just talked about is a strong base. Na is about right here, so if it forms with OH, it's going to be a strong base. A strong base is a strong electrolyte, so that's a yes. H2SO4, we have 4 minus 2 on the oxygens and hydrogens. Yes, that is strong. H3PO4, 4 minus 3 on the H's is not going to be strong. So this is not a strong electrolyte. And then we have strontium hydroxide, which is a strong base. And if it's a strong base, strontium is right here. So if it is part of the strong bases, then it is a strong electrolyte. So the only answer that is incorrect here is H3PO4. All of the others are strong electrolytes. If you are struggling with electrolytes, these rules are in the notes, and then the strong bases trick I've just taught you because this is the worst you're going to see it. I've looked through the test a few times now. This is the worst you're going to see it, and then we will continue to learn strong bases and strong acids in the next unit. Number 6, how do we increase the solubility of solid solutes? Increasing solubility. So, in order to increase solubility, we need to increase the heat. We need to increase the surface area so that the molecules can react with each other quicker. Increase heat. And we need to increase agitation. We need to agitate the solution. And agitation is stirring or swirling. Some of you may have gotten the iron filings question on our puzzle piece. So the reason for that is we can actually put a spinning magnet underneath those iron filings. So we put the iron filings into the solution and the spinning magnet underneath the beaker. And so that magnet will spin and it will make the iron filings go all the way through the solution and stir it up like really, really consistently. It's very interesting. You just have to not need iron in your final product. And that increases agitation, which increases solubility. Number 7, which version of a solution conditions increases solubility? So, increase the size of the crystal or decrease the size of the crystal? If it's smaller, it will dissolve faster. Good. Then we increase heat and increase stirring. Halfway. Okay. These conditions increase solubility. Making the size of the individual crystals smaller is going to make it dissolve faster. You got it. All right, and now we are on the calculations portion. So if you notice, this is a long test, okay? There are 18 questions on the test. I was able to combine 2 of them on the review to help speed up the review. Only the first 7 are all of those rules. And now the rest is calculations from E and F. So hang with me while we do these. Number 8, what is the molarity of a solution that contains 0.234 moles of solute in 300 milliliters of solution? So we're starting off easy here. We're just doing moles over milliliters, and we're looking for molarity. So we have to remember our equation here. Molarity equals moles over liters. So here, it's 0.234 moles over 300 milliliters. And 300 milliliters has to be converted to liters in order for this to be correct. So we have to move our decimal point 1, 2, 3 to convert it to liters. And now we're at 0.3 liters. Now I'm in moles over liters. After that, this is just calculator work. 0.234 divided by 0.3 equals 0.78. And and that is 0.78 molar. And that's it. Moles over liters. Did we get a decimal? Yes, and that's okay. You just need to know the process, and you need to trust your process, and then you can trust your answer. Number 9. What is the molarity of a solution containing 330 grams of NaCl in 1 liter of solution? Use sig figs. Lovely. So sig figs kind of come back on this test in that your answers start from here on are going to be pretty beautifully rounded. And it's going to give you 330 point and 1.00. Well, in both of those instances, those are 3 sig figs. So I know my answer must have 3 sig figs. And once I keep that in mind, the rest is going to take care of itself. So the molarity of a solution, M equals moles over liters. And so if I have 330 grams of NaCl, I need to convert that to moles. So I'm going to do 330 grams NaCl, drag down grams NaCl, and convert it to moles up here. All I need now is a molar mass. And so what I can do is take this entire answer and I can divide it by liters so that I only have to do one calculation. And I can see that 1 liter, so my final answer is just going to be this over 1. So really, I just need to convert to moles, divide it by 1, and that is going to be my answer in molarity. But first, I need the molar mass of NaCl. So I go to Na, I look it up, 22.99. I'm going to round that to 23.0 because of sig figs. And Cl is going to be 35.453. That's going to be 35.5. So now, using Desmos, I can put all of this into the calculator, and it's going to be nice and pretty for me. And I get 5.65. 5.65 molar. Done with that one, knocked it out. And I got 3 sig figs. Can I keep going? All right. Number 10. How many grams of solute are there in 250 milliliters of a solution of 3.693 times 10 to the negative 4 molar NaNO3, where the molar mass equals 84.994 grams per mole? Gross. This is gross. But when I follow my formula, I can figure out what they're asking. Grams of solute in 250 mils of a solution, and the molarity is given and a molar mass is given. So I remember that M equals moles over liters. And now I can fill in that equation based on what I've been given. I was given 250 milliliters. And so I can put that in for liters. All I have to do is move the decimal 3 times. So I can say that my liters down here is 0.250. And I was given a capital M molar of NaNO3. So I know that can go right here. My molarity is given to me at 3.693 times 10 to the negative 4. And so that means I'm looking for moles that I can then convert to grams. So what I have to do here is put an X in for moles so that I can solve for moles of NaNO3. And then I will take that answer and I will convert it to grams of NaNO3. And this molar mass was given to me, so it's really only 2 steps left and this problem is done. The first step is to solve for X. So I'm going to multiply by 0.250 on both sides. And that will give me X equals 0.250 times 3.693 times 10 to the negative 4. Put that in my calculator. And I get 9.23 times 10 to the negative 5 times 10 to the negative 5 moles of NaNO3. Well, now I need this in grams. So I need to take my moles NaNO3 and convert it to grams. So I take this answer, I have my unit moles NaNO3, and I drag down moles NaNO3, and 1 mole equals 84.994 grams of sodium nitrate. 84.994 NaNO3. So all I have to do to finish this out is multiply the answer I just calculated times 84.994, and that is going to give me my answer in grams. I get 7.8 47 times 10 to the times 10 to the negative 3 grams of NaNO3. A very small number, but it's correct because I can trust my process. Your answer won't even be this convoluted because what I did when I made this question, I kept the wording and I just changed this and this. So you need to know the process, but your numbers are probably going to look much prettier than mine. And that's okay. If you can do it with ugly numbers, then you can do it with pretty numbers. Number 11. A 35 milliliter sample of 0.10 nitric acid is needed to neutralize a 15 milliliter sample of potassium hydroxide. What is the molarity of the KOH solution? And here's the balance reaction. Okay, so when we see the word neutralize, we have to automatically think M1V1 equals M2V2. This is our other equation on this test. When we see neutralize, we think M1V1 equals M2V2. The other thing you need to realize is you are given one volume and one molarity, and another volume and a missing molarity. That means you have this variable, and this variable. You just need to solve for this one. And at that point, it becomes an algebra problem, which ain't that bad. Don't look at me like that. So now we just fill in our variables. A 35 milliliter sample of 0.10 nitric acid is needed to neutralize 15 milliliters, a 15 milliliter sample of potassium hydroxide. What is the molarity of the potassium hydroxide solution? So I'm going to do the nitric acid solution on one end. That's 35 milliliters. Sorry, that's the V. Let me line those up for you. And this one, I don't have to convert to liters because both are in milliliters. As long as your volume unit is the same on both sides, you don't have to change it. So I have 0.1 molar is my M1. My V1 is 35 mils equals my unknown. It says what is the molarity is going to be my X, that's M2, and my V2 is 15 mils. Now all I have to do is solve for X, and my answer is going to be the molarity of the KOH solution. I didn't even need this balanced reaction. Tricky. So I divide by both sides. I divide on both sides by 15. I have 0.1 times 35 over 15. Put that in my calculator here. And I get 0.2333 repeating. So I get 0.23 molar. And this is of the KOH solution. That one's not hard. It's intimidating at first, but once you understand which equation to use, you're just filling in these variables. Number 12. Consider the reaction of silver metal and nitric acid given the equation below. What volume of a 1.85 molar nitric acid solution is needed to completely react with 0.934 grams of silver? All right. And you have a balanced equation. When you have a balanced equation and you have a mass, it has to be a molarity problem because that mass has to be converted to moles. So we know we have a molarity problem, which is molarity equals moles over liters. So our unknown is going to be the liters. This is where we're eventually going to wind up. And we're given a 1.85 molar nitric acid solution. So we're going to do 1.85 molar equals, and down on the bottom, this is our unknown. But we don't have moles either. So this is another unknown that we can't solve for yet. I'm sorry. This is the unknown we can't solve for. We can't solve for liters yet because we don't even know moles in this problem. So in order to do this, we have to take this gram and we have to convert it to moles. But we can't convert it to moles of silver because we're talking about nitric acid. We have to go from grams of silver to moles of silver to moles of nitric acid. We have to use stoichiometry to go from grams to moles in order to do this. Because all of this is for nitric acid, which means silver has its own set of equation floating around in the background that we don't know about. We had to use the silver amount and stoichiometry to then convert to moles of nitric acid, and then we can get this problem right. That way we can get liters of nitric acid. So here we go. First, I have to do stoich here, and then I'll be able to use algebra to solve for x here. So what I have to do is get my mole map, and I have to go from grams of silver to moles of silver to moles of nitric acid. This is a two-step problem. I'm going to need the molar mass of silver, and I'm going to need the balanced chemical equation. So I do 0.934 grams of Ag and then I'm going to drag down grams of Ag, so I need my molar mass. That's going to be 107.868 grams of Ag. That will equal 1 mole of Ag. Now I take moles of Ag and I drag it down. I have mole of Ag on the bottom. And I need to arrive at mole of nitric acid, which is given to me as HNO3. And so here I fill in the coefficients from the balanced equation. Mole Ag down here is 3. And mole nitric acid on top, HNO3, is 4. Now I'm ready to solve for this so that this will give me the answer in moles that I can then use in algebra to get an answer in liters. So moles of HNO3 is going to equal that, and I need a fancy calculator. Isn't this exciting? So I'm using real Desmos now. 0.934 times 1 times 4 all over 107.868 times 3 equals 0.0115 moles HNO3. So that will go up at the top here. And now that I have a moles and a molarity, now I can use algebra to solve for liters. So I can erase this answer here so that I have space to do the algebra. Now, I need to get x by itself. And so I'm going to multiply by x on both sides of the equation so that it cancels here, and now it's over here. And then I will divide by 1.85 on both sides of the equation so that I have it there. And now, x is by itself. And so my equation to type in is 0.0115, the answer I got from stoichiometry, divided by 1.85, the molarity that was given to me. This is going to give me my final answer of nitric acid. How many liters do I need in order to make this equation run? I put it in the calculator, and I get a low number, and that is okay. I get 0.006245. Yeah, I'll just give it to you like that. 0.00624 liters. So if I were to convert that to milliliters, 1, 2, 3, that's about 6 milliliters of nitric acid. And at 1.85 molarity, that's pretty strong. And that's how you do that problem. But wait, there's more. So if you need to pause the video at any time, I totally understand. Just don't pause me in real life. But that's why it's recorded, because this is a thick test. This is even going to take me the whole period just to review it. So in order to finish it, you may need multiple days, you may need multiple times to open it. That's fine. Just come see me. And we may have time to do it in the period next week, hopefully. Number 13, a legendary chemistry teacher needs 220 milliliters of nitric acid for tomorrow's lab. Nice. When he goes to chemical storage, he finds 85 milliliters of a 6 molar sulfuric acid solution. Oh, that's a typo. It still needs to be nitric acid. He dilutes the solution to the volume he needs. What is the concentration of the diluted acid? When you see this, you should rejoice. When you see the word diluted, this is the dilution equation. M1V1 equals M2V2. So you should now have somewhere written down your magic words for M1V1 equals M2V2 are dilution and neutralize. We didn't use the neutralize word here, but we do have the dilution word here. And so that's our trigger word to use M1V1 equals M2V2. And so I need 220 milliliters of acid for tomorrow. So that's going to be my volume 2, because that's my desired final amount. Reading time. Good thing we're still here. When he goes to chemical storage, he finds 85 mils. So my original is my stock solution, which is at 85 mils. My original is also at 6 molar. Let me just fit this 6 in right there, just like that. So that my M1 is 6, my V1 is 85, my V2 is 220. I dilute the solution to the volume I need, which was 220. What is the concentration of the diluted acid? That is our X. M2 is our concentration. In order to figure this out, I just divide by 220 on both sides and put the answer in Desmos. Six times 85 divided by 220 equals 2.31818181, repeating. So I get 2.318. And that is molar. Those are a little easier. Almost there. Hang in there. Number 14. A chemist needs to make 250 milliliters of 1 molar HCl. The only available solution in the stockroom is 5.5 molar HCl. What volume of the 5.5 molar HCl, so we're looking for what volume, should be diluted to produce 250 mils of 1 molar HCl? Okay, so this 250 number showed up twice, which confused me for a minute. But both of those are our final volume. So I know I need to arrive at a 1 molar solution that is 250 milliliters. The only available solution in the stock room is 5.5 molar, which is insanely strong. What volume of the 5.5 do I need to dilute? So my volume, how much of my stock solution do I need to get out? And it's going to be in milliliters. So all I have to do now that I'm set up is divide by 5.5 on both sides to get X by itself. So when I do that, X equals 1 times 250 over 5.5. I'm going to need about 45.454545, so 45.5 milliliters of HCl. So in real life, I would get the 45 milliliters of HCl and then carefully dilute it with water to make 250 milliliters of my final product. So I'll just add water until I get to 250 milliliters, and then it will be perfectly at 1 molar solution. I will have my desired strength, and I will have my desired amount. All right, 15, 16, and 17. If you thought this was painful before, now we are predicting products of chemical equations, and they are word problems. So we are going to need to remember a lot of our rules from the first semester. Here we go. Predict the products of the following chemical reaction and whether a precipitate is formed. So I have 2 KOH plus calcium chloride. And nice, on this side they already balanced for me, so I can kind of see where I'm headed. Well, this is a double replacement reaction. Every single reaction where you're asked to predict these products, they're going to be double replacement. Okay? That means we need to keep, let's say we have A, B, C, D. We need to keep potassium and calcium where they are, and we need to switch OH and chloride, so that we get AdCb as our products. So here's what that looks like. Let me make sure this is still recording. Okay. So I need to keep potassium in its place and calcium in its place. But now this chlorine needs to go to potassium, and I have to match up their charges and make sure nothing cancels. Since potassium is in the first group and chlorine is in the 17th group, this charge would be +1, this charge is -1, they cancel out. I do the swap and drop, it is KCl. All right. And then I have calcium hydroxide, CaOH. Well, hydroxide is 2 elements, so it is a polyatomic ion, and it comes with a -1 charge. So the -1 charge will drop down to the calcium as a 1. And the calcium's charge, it's in the second group, so it is +2. That charge is going to drop to the entire hydroxide at the bottom, so that these are our final products. potassium chloride, and calcium hydroxide. Now that I have these products, I need to balance them. I have 2K and 1K here, so I need 2K here. And then that 2 takes care of this chlorine 2. And then I have calcium and hydroxide, where I have 2 OHs and 1 Ca. That is taken care of. So these are my final products. And now I need to say which one is a precipitate. So I go to chlorine. I find chlorine, and I see that chlorine is soluble unless it's with Ag, Pb, and Hg. None of those are K. So potassium chloride is going to dissolve. This is not a precipitate. When I look at calcium hydroxide, I go down to OH. OH is insoluble unless it's with compounds of ammonia, the first group, calcium, strontium, or barium. Well, calcium is what I have here, so OH is insoluble unless it's with calcium, which now makes it soluble. So both of these are soluble and no precip is formed. Golly gee willikers. Two more. Number 16. A solution of silver nitrate, AgNO3, is added to a solution of sodium chloride, NaCl. Write the correct balanced equation with products and states of matter. So, solid, liquid, gas, and aqueous. This is basically the same thing. We have to predict the products, and then we have to say which one is aqueous and which one is still a solid, or which one is going to become a solid. Both of these would be aqueous from the last problem. Number 16. Write the correct balanced equation. So I have silver nitrate, AgNO3 is added to a solution of sodium chloride, NaCl. I do another double replacement, so I'm going to keep Ag right where it is, and I'm going to keep Na right where it is. But now chlorine is going to come over to the Ag, and chlorine has a -1 charge, so it brings a 1 over. But silver has a +1 charge. Oh, that's nice. So silver has a +1 charge, and it will also give the 1 to the Cl, so this is exactly how it needs to be. Then I look at Na. The NO3 now needs to come over to the Na. So I have NaNO3. And sodium is a +1 charge, and that's good. And NO3 is a -1 charge, and that's good. So swap and drop, everything cancels, it's fine. All I had to do was switch places, which means everybody's already balanced. And so this is finally balanced. Now I know these were solutions, so these were aqueous when they started. And AgCl, I have to get onto my chart here, and I see that chlorine is soluble unless it's with Ag. So that means it is insoluble and it is a solid. And then NaNO3, I have to look at NO3 on my chart, and NO3 is always soluble, no exceptions, which means it remains as aqueous. The only time you will use liquid is if it's water. The L only goes on to pure H2O, and then the gas will only go on to gases, which is usually the diatomic molecules. You're not going to have liquid and gas on this test in that way. Last one, number 17. The same thing. A solution of barium chloride is added to a solution of lead 2 nitrate. Write the correct balanced equation with products and states of matter. This time, and this will be on your test, you have no equation or formula given to you. It's all words. So barium chloride, that's Ba and Cl, Barium has a charge of +2, so it's going to give this 2 to the Cl. And chlorine has a charge of -1, so it gives the 1 to the barium there, and they do not cancel beyond that. It is BaCl2. And I know it is aqueous because it told me it is a solution. Next, I have lead 2 nitrate. And so the Roman numeral tells me that I'm using Pb with a 2+ charge. And the nitrate tells me I'm using NO3 with a -1 charge, which is in the polyatomic ions list on your test. I find nitrate, and it is NO3 minus with a it's a NO3 with a -1 charge. So the 2 from the Pb is given to the entirety of NO3, so it's going to look like this. Pb NO3 with a 2 down underneath, and the 1 on NO3 goes to the Pb and disappears, and this is also a solution, so it is aqueous. Now I'm ready to form my products with the same double replacement steps. So I'm going to keep barium in its place, and I'm going to keep lead in its place. So barium now gets to bond with NO3. Remember, barium had a 2+ charge, so it is going to give that 2 to the NO3 right like this, and NO3 has a 1 charge that it gives to the barium, and we're good. Then I'm going to do lead. I have Pb, and the Pb is going to go with the Cl. Now, I know I have lead 2 nitrate, so I know I'm still using Pb2+, and Cl is 1-, so I go PbCl2. And then I look in my solubility chart. Chlorine is always soluble unless it's with Pb, so this is a solid. And then I look at barium nitrate. Barium nitrate, NO3. NO3 is always soluble no matter what, no exceptions. So this is still aqueous. I check to make sure it's balanced. Ba, Ba, Cl2, Cl2, Pb, Pb, NO3, 2, NO3, 2. It is balanced just like this. That is it. That is the end of the review. I wish you Godspeed on this test. I wish you Godspeed for even watching the entirety of this video. Good luck. You're going to do fantastic. I believe in you.
I do.